Looking at the history of this transmission and maybe how they name it and number it and all that stuff, this transmission, the 41TE, actually came out in 1988 and a half in a Chrysler New Yorker. And it was like the first fully computer controlled transmission I think that any automotive manufacturer provided. And it was a horrible transmission. It failed miserably. There were class action lawsuits. All the manufacturers were quick to point their fingers and say how bad they were and say that they had basically a pile of junk on their hands. But Chrysler back then, yeah, I'd have to give them credit. They did not give up on it. They enhanced it. They improved it quite a bit. A lot of improvements over the first few years. And then one of the biggest changes came in 1995 when they redesigned the computer. They made it adaptable or programmable, should say, so they can do updates. Before they'd have to just change a computer out for the if it needed to be updated or they had better software. Now they're able to electronically erase and reprogram the computer, and that the software really made this transmission so much better to the point where they still have this transmission in 2018. The Dodge Journeys use this transmission, some of them still, and it's still being used, a little 4-speed transmission. And then around, I'm gonna guess it was around 2010, they came out the 68 or the no 61, 62 TE, and it's the 6-speed version of this. And it's basically the same transmission that you guys are gonna learn about right here. That has the same input drum, same set of 5 clutches, but what they've added on the 6-speed is they added what they call a compounder clutch and a direct clutch, and that gives us the ability of getting a couple more gears. So they basically took the 4-speed and they added another planetary gear set, another clutch assembly, and got a couple more extra gear ratios out of it. And they still use that in 2018 on some of their models. But here on this slide, I'm trying to let you guys understand their naming and what they're trying to accomplish here. This right here is pretty much what we're talking about, 41TE transmission. The 4 means it's a 4-speed. 1 is the relative torque capacity, and actually 0 is where they start. It goes from 0 up to basically 9, but I don't think they have any transmissions that have the 9 designation. But some of the smaller, even for example that Dodge Journey that I just mentioned, it's going to have a 40 TE in it. T means it's transverse, and E means it's electronically controlled. In the old days where they had like a 31 TH, you can imagine what that is. That's a 3-speed. 1 was the relative torque capacity. It was transverse, and it was hydraulically controlled. It used a throttle valve and a governor valve. It didn't use solenoids or anything like that. Now this is a pretty common transmission that they use right now. It's a ZF built transmission. The reason why I point this out is because it kind of breaks the mold and when they were naming this. It is a 9-speed, but their torque capacity is 48, and it's like 48 out of 100 most likely. The reason why they use the 48 is because this is a ZF transmission, and their designation is a ZF it's a 9 HP 48. So I think they just carried the ZF terminology over to their terminology, and it is still transverse and electronic. To give more examples, they do have, some of you might have heard of a 48RE. It's a 4-speed, relative torque capacity is 8, so that's pretty high up there. That's what they would put in like the diesel trucks in like the late 90s, early 2000s. Then rear-wheel drive, electronically controlled. And I put this one up here because they replaced this 4-speed transmission with the 68 RFE. It's a 6-speed, relative torque capacity of 8, rear-wheel drive, but they threw this F in here. And the F means fully. So the 48RE was an electronically controlled transmission, but it wasn't fully electronic. It had a throttle valve still. So when you gave it, actually, the 48RE had electric motor externally mounted, but like the 47RE and the 46RE, the 44 and the 42 REs, they had a physical cable that went up to a throttle actuator, and it changed the throttle valve in the transmission. So when they got rid of that cable, they added the F. So instead of calling it 68RE, they call it a 68RFE to let you know that's fully electronically controlled. So it's a little confusing, and they kind of, I think when they went to it, they said, oh, okay, we're going to have this common naming structure, and then as it went along, they kind of had to fall away from their common naming structure because they wanted to be clear. And they've got other transmissions like the 42 RLE, 42 4-speed, 2 is the relative torque capacity, rear wheel drive is R, L longitudinal, so it's front rear facing, and then E electronic. But the big thing is that first number is the speeds, and the second number is going to be its relative torque capacity, whether it be 2 digits or 1. And then it's going to be a transverse or rear wheel drive or longitudinal if it has an L in there. Then E just means it's electronically controlled, which pretty much anything is going to be electronically controlled unless you get real dated with your stuff there. So on this slide, we're looking at a range reference chart, and a range reference chart will basically show what clutches are on in the different gear ranges. I've got park, reverse, neutral, and when we're in the overdrive position on the gear selector, we have available first, second, direct, which is really third gear, and overdrive, which would be fourth gear. So this range reference chart will show us what clutches are applied for those different gear selections. As you can see here, I've got 5 clutches total: underdrive, overdrive, reverse, 2/4, and low reverse. The input clutches are underdrive, overdrive, and reverse, and the holding clutches are 2/4 and low and reverse. The input clutches basically mean that anything that's an input clutch is going to deliver torque from the engine to a gear set part, rotational torque, through the torque converter. And a holding clutch is going to be a clutch assembly that is going to take part of the gear set and hold it to the case. So if we take a look, like for example in reverse, we have a reverse clutch applied, that's going to be driving a gear set part, and we have a low reverse clutch that's applied, that's going to be holding a gear set part to give us reverse. And we'll see this when we go through power flow. Then in first, we have the underdrive clutch and the low reverse. You can usually tell by the names of these clutches what they're doing. Underdrive clutch for second and the 2/4. You can see it's underdrive would be used in most underdrive gears, and then the 2/4. The direct, if you remember our gear set rules, if we don't hold anything but we drive 2 parts of the gear set, we can get direct drive. So that's what they do, is they apply the underdrive and overdrive clutch, and they don't hold anything. You can see neither of the holding clutches are applied. And then when we shift into fourth gear, the overdrive clutch applies and the 2/4 comes back on. One thing to note when you're looking at a range reference chart like this is that they're usually only releasing one clutch and applying one clutch at any given time. So if we think of first gear, we have underdrive and low reverse. When we shift from first to second, I'm releasing the low reverse and applying the 2/4. So I don't have to deal with the release of one clutch and the apply of another. Then when we shift from second to third, we release the 2/4 and apply the overdrive. And then when we shift from third to fourth, I release the underdrive and apply my 2/4 again. So that kind of keeps it simple as far as I'm not releasing too many things or applying too many things at any given time, that they're just controlling the release of one clutch and the apply of another. And where a range reference chart really helps you out is, like, let's say this transmission doesn't have, let's say for example, second and fourth gear. Well, we know that the 2/4 clutch is responsible for that. Or if the transmission doesn't have reverse and it doesn't have drive, but maybe I could command it in the second or third or fourth and get that to happen. Well, okay, we're going to be looking at the low reverse clutch. So when we look at the symptom that the vehicle has, we're going to look for any common single component that may cause all of the symptoms. So that's where the range reference chart will help you. This is a pretty simple range reference chart. We've only got 5 clutches, and they're not that, it's not that hard to figure out. Some range reference charts get pretty big when you're talking about what's happening with sprags and rollers, and they might have more than just 5 clutches. They might have, I think there's some transmissions out there have up to 13 things basically on their range reference chart. A lot of stuff going on. So, but it can help us in our diagnostics. Just a simple slide here that just shows the gear ratios. You can see first 2.84, second 1.57. There's our direct drive for third, and our overdrive is 0.69. Our reverse gear is 2.21. These are the gear ratios that we're getting through the gear set. It doesn't include the final drive that you'd have in a transaxle. This right here is a picture of the input drum. It's a cutaway. We have this out at school. And the input drum, if you remember, we have these 3 clutches: underdrive, overdrive, and reverse. And they're laid out. This is obviously not how it's look in a normal transmission because I cut this window out right here. But the furthest most, this is the input shaft right here. So that's the input from the torque converter. And then these little hubs here will drive the gear set parts. So like this is the rear sun, and this is a carrier / annulus assembly, the splines for it. So I have an underdrive clutch. It's the deepest in there. This underdrive clutch actually right here is connected to, let me just erase this. This underdrive clutch, this is right here. When it's applied, it's going to be driving this sun gear assembly, the rear sun. And my overdrive clutch, when it's applied, which is this clutch is kind of sandwiched in the middle right here, when it's applied, it drives this hub, and on this hub we have the front carrier rear annulus assembly. The annulus, ring gear, internal gear, whatever you want to call it. And lastly, the reverse clutch, which only has like 2 friction discs. It's between these 2 plates right here. And I don't have the hub installed, but there's a hub that kind of fits right inside there, and it drives the front sun gear. We'll see these connections here on these slides coming up. So, but the big thing is all in my input drum on this transmission, it's pretty simple setup. It's about as easy as it gets. All my input clutches are located in this one drum right here. This right here, if you're wondering, is the tone wheel for the speed sensor, the input shaft speed sensor. So now this is the gear set. Now I know you can't really see any of the gears that are on here, but what it's really showing you are the hubs. That on that previous slide I had the input drum assembly shown, and if you remember, you saw the underdrive, overdrive, and reverse clutches were in that input drum. Well, that input drum would fit right around this whole section here. So that's the idea of what we're looking at here, is the input drum with its clutches grab onto these 3 hubs. And the deepest clutch assembly in the input drum was the underdrive clutch, so it has the ability of grabbing onto that hub. That hub comes all the way in here and drives the sun gear located in the back. The middle set of clutches grabs onto this middle hub assembly, and it goes in and grabs this it's actually this assembly here, but this is a front carrier rear annulus assembly. And then lastly, the reverse clutch grabs onto this whole shell assembly. I know it's kind of odd to see it like this, but this is one big shell assembly, and there's a front sun gear inside there that's welded to that shell assembly. Now those are our driving clutches where they would drive. You could see that's why they're kind of all a little bit smaller. The hubs are smaller in diameter, because around this whole hub assembly is going to be the input clutch housing. That's going to turn around and grab onto those hubs and drive those gear set parts. Now these 2 hubs right here, you can see there's splines there, and if you can imagine, the clutch discs, the friction plates are the ones that grab onto these parts. You can see where they've worn into the overdrive clutch assembly here, and you can kind of see the little marks on this 2.4 clutch hub as well. But these are our holding clutches, and there's only two of those in this transmission, the 2-4 and the low reverse, and they basically will have friction discs that go between the transmission case and these hubs. So we'll have pistons that will apply these things independently. They'll be like right where I drew those red lines. Those are clutch discs, and there'll be a plate that's kind of locked into the case that separates those two. Now I have a low reverse piston coming from the bottom of the case, squeezing the low reverse clutch pack, and I have a 2-4 piston coming from the middle of the case, squeezing the 2-4 clutch pack. So that's how we're able to hold these gear set parts to the transmission case, is through a 2-4 clutch and through a low reverse clutch. When it applies, it locks these gear set parts. It locks the 2-4 clutch will lock the front sun, and the low reverse clutch will lock the front carrier rear annulus assembly. And we'll see more of that coming up. Matter of fact, I got a nice little kind of block diagram that shows how this all assembles, and hopefully will work to explain power flow. This is that same gear set that you just saw, but I've taken it apart so you can see those pieces, and I kind of put notes on there where these clutches are grabbing. So these are kind of like the common connections. Kind of going off the bulleted list here, my underdrive clutch. My underdrive clutch in the input drum is a driving clutch, and you can see right over here, this is where the underdrive clutch grabs onto. And when the underdrive clutch is applied, it's going to take input torque through the input drum assembly and deliver it to that rear sun gear. The overdrive clutch assembly is that middle clutch pack in the input drum assembly, and when it applies, it's going to take engine torque and deliver it to this assembly. On the top half of this gear set, we have the carrier, like a front carrier, and on the rear half of the gear set, we have an annulus gear. So it's a combined, that overdrive clutch has the ability of, when it drives one, it drives both. So we're driving part of the front gear set and the rear gear set when we do that. A front carrier and then a rear annulus. Chrysler likes to call their ring gears annulus, so to kind of stick with their format, I'll try to keep to that as well. The reverse clutch is going to be applied in reverse, and the reverse clutch grabs onto this part. That's the outermost clutch assembly in the input drum assembly, and when it applies, it's going to apply torque to that front sun gear right there. So that's welded to this whole shell assembly. So this is our output gear set, and you can see on the very bottom, this is a kind of a helical cut gear I've got there. That helical cut gear is like a transfer gear. It takes the torque and transfers it to the transfer shaft, which then drives the final drive assembly. But connected to the output gear assembly, we have a rear carrier and a front internal gear. So it's kind of like the this assembly over here, where I've got part of a front gear set and rear gear set connected to the same, in this case, the output shaft. So when you put all this together, it looks like the assembly on the previous slide. And at school, we have all these gear sets on stands so you can spin them around and so forth. Take them apart and get your hands on them and get a better understanding of what you're looking at. As far as the holding clutches, and this is the same picture that we have on the bottom, but if you notice on the previous slide, I didn't mention the low reverse and I didn't mention the 2-4, because if you remember, those are holding clutches. Those are going to take these gear set parts and lock them to the transmission case. Kind of going back to those Planetary gear set rules. If you input one part, hold a part, that third part's going to be the output, and it's going to be at some kind of a gear reduction or overdrive or reverse. So looking at the 2-4 clutch, it's applied in second and fourth, and this larger set of splines that we have right here, they're going to house the friction discs. They're going to hold the friction discs are going to lug onto those splines, and when the 2-4 clutch applies, it's going to lock this front sun gear to the case. Now if we look at the low reverse clutch assembly right here, it's got a larger set of splines as well, because they will take the friction discs between these set of splines and the transmission case. That's actually the very bottom set of clutches when we take this transmission apart. And when that low reverse clutch applies, which is done in first and reverse, we're going to lock this rear internal, which is back there, the back half, the rear internal, and the front carrier, which should be on the front half of the gear set. We're going to lock that to the transmission case so it can't move. So this is a little block diagram representation of the gear set. If I were to draw a line down the middle and say, yeah, I've got two planetary gear sets. This would be my front planetary gear set. This would be my rear planetary gear set. And to make sure everybody understands what they're looking at, in the middle is our sun gear. It's like we would always imagine the sun gear being in the middle. And then what connects to the sun gear is going to be our carrier, their little pinion gears. So imagine that's the sun in the middle, the little carrier gears, the little pinion gears or planet gears are meshing with the sun gear, and then our outermost gear would be the internal gear. Now I tried to color code this so that way common connections are common connections. So if we just take a look real quick and see what we're looking at here, and some of these following slides do the same thing, but I'm going to go ahead and say it first here. On our front gear set, we can see we have an input carrier or input internal gear connected to a rear carrier assembly, and that is our output. And then I have a front carrier assembly which is connected to the rear internal gear assembly. And that not only has the ability of being getting held by the low reverse clutch, but also has the ability of being driven by our overdrive clutch. Obviously, they can't do that at the same time, but in overdrive or third and fourth, they can apply the overdrive clutch, and in first and reverse, they can apply the low reverse. So they can either hold that front carrier rear internal gear assembly, or they can drive that front carrier rear internal gear assembly. The underdrive clutch has the ability of going all the way to the back of this transmission and driving this rear sun gear kind of independently. And my reverse clutch has the ability of driving my front sun gear, and the 2-4 clutch has the ability of holding the front sun gear. Once again, they would never do those at the same time. You can't drive and hold apart at the same time, so reverse clutch would only be driving in reverse, and that sun gear would only be held in second and fourth. So that's how this gear set block diagram is laid out, just in a nutshell. But I'm going to go through and build it up piece by piece here on these next slides. This is, as I mentioned before, our driving clutches are these three coming in from the left. The arrows coming in, basically meaning that my engine torque has the ability of literally driving those clutches through the torque converter. And then my holding clutch is the one showing arrows pointing towards the transmission case. To kind of carry on with that discussion, here I've separated out the output component of the gear set and realize once again that this is the front half of the gear set, this is the rear half of the gear set. This is all connected to my output assembly. You can see it says output right there. And so if I were to look at it, it's this picture right here. So this would be the teeth on the annulus gear. I don't really see the teeth, but imagine, these are teeth right there. And that is connected to the rear carrier. And these are the little planet gears that we would find on the rear carrier. All of that is connected to the output shaft. And that little block drawing is basically representing this assembly right here, where we see the rear carrier and we see the front annulus gear. Now we add to that where we would have the front carrier and rear annulus gear, and that assembly is right down here. I know you really can't see those gears in there, but trust me, they're in there. The front half of the gear set would have the carrier assembly, and the rear half of that gear set has the internal teeth, the annulus gear, just like is drawn here on this picture. So what we do is we have the overdrive clutch through this hub right here. That's being represented by this arrow. So that overdrive clutch has the ability of driving this front carrier rear annulus assembly. And then the low reverse clutch, it has the ability of holding this front carrier rear annulus gear assembly, and it's done through the low reverse clutch. It can grab onto that set of clutch splines down there on the back of the gear set and hold that steady to the case. So the rear annulus can be held by the low reverse clutch or driven by the overdrive clutch. Now we add to it the front gear set, the front sun gear, and you can see once again it has the ability of being held by the 2-4 or being driven by the reverse. And that is this assembly. It's represented by this assembly in this picture down here. So my reverse clutch can grab onto the small set of splines and drive the front sun gear, or my low reverse, cross that out, or my 2-4 has the ability to hold on to this shell assembly, and obviously it's going to be done in second and fourth gears. Then finally we have our rear gear set, our rear sun gear, and the underdrive clutch can come in there and reach all the way to the back and drive that rear sun gear. So that completes our gear set. This picture right here represents that. So you can see my underdrive clutch would, when it's being applied, it will take engine torque and deliver it all the way to the back through that shaft to that rear sun gear. So we have our rear sun gear, we have our output gear set, we have our overdrive carrier and annulus gear assembly, and then we have our front sun gear assembly. It's all there. Now the thing is, when I cover power flow on this transmission, it's much easier to explain it using this drawing than it is to try to show it using just a big chunk of metal sitting there, especially when you have it all together. All you see from the outside are these splines, and you don't have any reference to what part of the gear set it's drawing unless you memorize that. So on these future slides coming up here where we go through power flow, I'll be able to point out pretty much just, okay, what are the gear sets being driven, what's being held. And for every gear except for second gear, they're really only using either the front half of the gear set or the rear half of the gear set. So it's really simple. It just comes down to a simple planetary gear set. You know, those rules that we followed, where a small gear is driving a big gear, you get a gear reduction. A big gear driving a small gear, get an overdrive. If you ever hold the carrier, you're going to get reverse. If you know, just an internal gear, just all these little planetary gear set rules. If a carrier's output, you're going to have underdrive. If a carrier's input, you're going to have overdrive. So it all really breaks down to some of those simple gear set rules, and we'll see that here on these power flow discussions coming up. So this transmission here is shown while we're in first gear, and only thing that we have that's applied is we have our underdrive clutch and our low reverse clutch. So torque comes in and it drives this rear sun gear, and then we hold our rear annulus. So we have our input is our sun gear is input, our carrier is output, and our internal gear is held. Hard to draw with a mouse, but so it's a small gear driving a big gear. That's the best gear reduction we can get, or the smallest gear driving the biggest gear. That's the best reduction that we can get, and that is what we use for first gear. This front gear set, if you also remember one of those gear set rules, it said that if you have something applied or driven but nothing held, that's neutral. You have to have something. You have to either have two parts input, or you have to have something that's input and something that's held. Because if you have two parts input, you have direct drive. If you have something input and something held, you've got a gear reduction or an overdrive or something like that. But if you have something input and nothing held, that gear that's not being held is just idling along. It doesn't have any torque transferring through it. If you have something held but nothing input, the gear that extra gear is just basically doing the same thing, it's idling along. So in this front gear set, yeah, we have our annulus gear is hooked up to the output shaft, so that's output, and we are holding our front carrier, but we're not doing anything with our front sun. So even though these parts are still spinning and moving, that front sun gear is just kind of idling along. So we'll see that with most gears. The only gear that this doesn't apply to is second. Second actually utilizes both gear sets. Now here's something that you want to remember for second gear. Because when we think about how first gear operates, we've got the sun gear that's rotating at input shaft speed, right? And we've got our annulus gear being held. And our output is coming from our rear carrier. When we shift this transmission in the second, we're still going to be driving our rear sun gear. We're not going to hold our internal gear anymore. What we're going to do is we're going to energize we're going to apply the front sun gear. And when we apply this front sun gear, what's going to end up happening is this rear annulus is going to start rotating a little bit. It's not going to go at input shaft speed, but it's going to go at a reduced speed. But what that ends up doing is instead of having this part held like we did in first, we now have the rear annulus rotating a little bit, and that steals a little bit of that gear reduction away from first gear, and that's how we end up getting second. So second gear is the most complicated, but if you really, as far as trying to understand how power flow goes, but if you really stop and think about what's happening, my sun gear is in first gear, my sun gear is input, and my annulus is held. And in second gear, all I do is activate this front gear set to let my rear annulus start to rotate a little bit at a certain speed. And by not holding it directly, I steal a little bit of that gear reduction away, and that gives me what I have in this transmission as second gear. So now here we are talking about second gear. Output is from both gear sets, so I need every gear in this gear set assembly to work. When I was in first gear, I could literally be missing parts of my front gear set and I would still have first gear. But in this case, I need everything available, because what ends up happening is I'm holding a part of my front gear set through my 2/4 clutch, yet I'm still driving a part of my rear gear set through the overdrive clutch, or underdrive clutch, sorry. So what we're looking at though, and as I mentioned on the previous slide, in first gear where this was held, that's not going to be held anymore. It's going to be going at a little bit of a gear reduction. But it's going to be rotating with the input shaft, but not input shaft speed. It won't be going as fast as input shaft speed. The sun gear is yes, it's going to be, the rear sun gear is going to be going input shaft speed, whereas the front or the rear annulus gear assembly is going to be going something less than input shaft speed. That causes this rear carrier assembly to rotate at a gear reduction, but not as good of a gear reduction as first has. Third gear is pretty simple. If you remember direct drive on a transmission, you have two parts input, nothing held. So that's the reason why we don't see anything connected to the transmission case up here. So I still have my underdrive clutch applied, even though they just call it underdrive clutch, even though third gear is not underdrive. But I'm literally applying and driving my sun gear like I did in first and second gear. But what I've done now is, after I release the 2/4 clutch, I'm taking my overdrive clutch and I'm going to drive the front carrier rear annulus assembly. So my rear annulus assembly is going input shaft speed, my rear sun gear is going input shaft speed. You can imagine that's going to force the rear carrier to go input shaft speed. I put that as output, but is also, since this is going the same speed as this, since the rear sun and the rear carrier internal or annulus gear are going the same speed, it's going to force the rear carrier to go the same speed, and that's direct drive. And if we also stop, the way they achieve that is by releasing the 2/4 clutch and applying the overdrive clutch. And that is the two clutches that they deal with when we shift from second to third. Now we're in fourth gear, and The two clutches that they deal with fourth gear is they will release the underdrive clutch. So now this isn't doing anything. And they'll reapply the 2/4 clutch. And if we think of what half of the output is coming from, in this case it's going to be from the front gear set. So here I got my front gear set. I'm holding a part of the front gear set with my 2/4 clutch. I am driving a part of the front gear set with my overdrive clutch, and then my output is going to be my front annulus assembly. So in this case I could actually be missing parts of the rear gear set and I would still be able to get fourth gear, because all the planetary action that's occurring is coming from the front gear set, and it's just done with just the sun gear as held, a carrier as input, and the annulus gear as output. This also goes back with our gear set rules. If the carrier is ever input, overdrive must result, and the reason why is because it's the biggest gear in the gear set. I know it's located within, kind of inside the annulus gear, but it acts as the biggest gear in the gear set. So if I'm ever having my overdrive clutch as the input, I'm going to have an overdrive as a result, as long as I have a different part held. The best overdrive I would have is if I held my internal gear, which obviously you can't do in this case because that would be the spline to the output shaft, where like the best overdrive you could possibly get out of a planetary gear set would be drive the carrier and output the sun, because it would be the biggest gear driving the smallest gear. But that overdrive is a little excessive, very excessive. It'd be like a 0.4 to 1 overdrive. In this case, they're doing about a 0.7 to 1 overdrive, and they get that by inputting the carrier and outputting the medium-sized gear, which is the annulus. And now we finish up with reverse. The output is actually from the front gear set on this, and this could be confusing to some because when you look at this, you're saying, wait a minute, I'm holding a part of the rear gear set here with the low reverse clutch. But if you remember, everything that has the same color is the same connection here. So we're holding the back of the gear set right where the rear annulus is, but it's also connected to the front carrier assembly. And if you remember that planetary gear set rule, that if the carrier is held, reverse must occur, that's what's occurring in this transmission. We're using the front half of the gear set. Our front sun gear is the input. Held is our front carrier assembly through the low reverse clutch, and then output would be our annulus gear, our front annulus gear. So all of this action that's occurring in reverse is happening on the front half of the gear set. So just as a recap, we have 3 driving clutches: our reverse clutch, underdrive, and overdrive clutch. Those are all located in the input drum assembly. And I have 2 holding clutches, and those clutches are located in the transmission case, and they are going to hold a gear set part, prevent it from spinning. And my low reverse clutch holds on to the rear annulus and the front carrier. The 2/4 clutch holds on to the front sun. Reverse clutch drives the front sun, underdrive clutch drives the rear sun, and my overdrive clutch drives my front carrier rear annulus assembly. 5 clutches, not too difficult to understand. No rollers, no one-ways, sprags or diodes, diode type, ratchet type clutches, nothing fancy, no bands. So it's actually a really simple, compact transmission. Now we're going to get into the electronics, and this is just a simple schematic here. It's not the most modern schematic, but the reason why I use it is because it does really still show everything that this transmission needs and uses. The one big thing that's different is it's got a it doesn't show like CAN bus or something like that or anything like that. But these transmissions throughout the years, they've pretty much have used the same inputs and the same outputs, so even if I had a modern drawing, it wouldn't have changed. And the reason why I like to use this one is because it puts the whole schematic with just the transmission related stuff on one page. So then what you're going to see on these next slides is I'm going to have call outs where I'm going to be pointing out all these different little aspects of this schematic, and we'll talk a little bit about them individually. As far as scan data and doing diagnostics, a lot of times the PCM will include the transmission functions. Sometimes you'll have a separate TCM. The earlier 41 TEs used to have a separate TCM. And then around probably 2000-ish, the next generation controllers that they called them back then, I don't know what they call them now, they included the TCM functions in the PCM. So that's pretty typical, pretty common. But you know, with any given vehicle, you could find it's got separate TCM and they just communicate to each other through a network. Or at times you're going to find that is what makes a difference between an ECM and a PCM. If I have a PCM, typically you're going to have the engine control and transmission functions in that one module. If you have a PCM, you're going to have both. If you have an ECM, you should have a separate TCM. ECM, engine control module, TCM, transmission control module. But regardless, it doesn't make a difference. This is a topography that you would see using like YTEC or the Chrysler, the Fiat Chrysler scan data. Here we can see we have a PCM, and they do have a TCM listed, but it's grayed out. If it's grayed out, that means it doesn't come with a TCM. So maybe they had a transmission option for this vehicle that utilized its own little separate TCM. But in this case, we have a PCM, and it's going to include our transmission functions. If you see the little lightning bolt next to it, that means that there is a flash available, so you're able to reprogram that. And this topography kind of just shows all the network connections. This is a CAN bus type system, so all of our CAN bus type network modules are going to be communicating on it. We have a gateway module, the total integrated power control module, common gateway. So we'll be able to speak with different buses, like low speed buses can communicate to the high speed buses. But like on this vehicle right here, not that this is a communications discussion or anything like that, but basically everything over here is going to be hooked up to a CAN bus network. And you can see by using the scan tool which ones are communicating. They would turn red if they weren't communicating, if there was an issue with them. And so that just shows, I was just going to mention that we've got like in this vehicle, our Dodge Charger that we have out here at school, it's got a 42 RLE, which is basically the same thing as a 41 TE. It's just the rear-wheel drive version of it. And so we can kind of look at some scan data and some functions related to that transmission on this vehicle. Input and output sensors. Some of the input sensors that we will find that are going to be pretty common across all these vehicles with 41 TEs is we're going to have a throttle position sensor, an input speed sensor, output speed sensor, shift lever position sensor, transmission fluid temp, and then we have some pressure switches. Now the outputs are pretty simple. We got a solenoid pack, and then we've got a relay. There are other things, like you can say output is going to be like the indicator lights or diagnostic scan tool, that kind of stuff, but these that I have listed up here are pretty much what make this transmission operate. If we were to start with the throttle position sensor, and you guys have, I'm sure, learned all about these things in previous classes, so we don't need to spend too much time on it, but on a throttle position sensor, you're going to have power going to it, 5 volts going in, you're going to have a ground, and then the little wiper blade on there is going to sweep across this resistor assembly, and depending on what voltage it picks up, if there's 5 up here, 4, 2, 1, depending on where it picks up on that voltage drop is going to be an indication of what your throttle position sensor signal is. And how does it affect transmission operation? It has a big influence over its shift timing and the shift quality. And the difference between those two is the shift timing would be like miles per hour. Like what mile per hour did, I'm going to write down there, MPH, did the transmission shift. And you can imagine a throttle position sensor is going to provide input on how much throttle you're giving it. So if I'm driving it around and giving it 10% throttle, my upshifts are going to be relatively early. I'm not looking for performance, I'm just cruising through town. Whereas if I'm at 90% throttle or 100% throttle, it's going to let the engine RPM climb much closer to its red line, to its peak power and torque curves, and it's going to be shifting me at higher RPMs. So the throttle position sensor is going to be kind of an input to the load that we are placing on the vehicle, and it will delay our shifts accordingly based on that. And the shift quality is going to be kind of along those same lines. It's going to be the feel. Shift quality, another way to think about that would be the feel of the shift. Is it harsh? Is it soft? So when we talk about shift quality, we think of the shift feel, slipping or banging in the gears. The throttle position sensor signal also plays a role on that, because I'm going to try to apply these clutches quicker when I'm under load. I realize I got to get fluid into those clutches quicker because there's going to be torque transferring through it, and I'm going to need to get that clutch to apply with more force, or else I'm going to slip through it and I'm going to cause a shift feel complaint or shift quality complaint. Whereas the same thing goes along if I'm just a 10% throttle, just cruising through town. I don't need to be banging into gears, so I'm going to let the fluid enter these clutch assemblies a little more gradual. And you know, the magic number I always put out is about 400 milliseconds. That's how long a shift should take, whether you're just cruising around slow, light throttle upshifts, or you're wide open throttle. And it's because of the RPM change. If I'm just light throttle upshifting through town, my RPM is just changing a few hundred RPM. But if I'm wide open throttle racing, my RPM changes, I might be doing 2,000 RPM changes between shifts. So I need to have both of those, whether I'm at wide open throttle or just cruising, to happen around 400 milliseconds. And if I do that, the shift will probably feel just fine. If this goes bad, what these 41 TEs do, if I have a throttle position sensor that has failed on the 41 TE, it's going to substitute a value. Usually it's 1/3 throttle. So you're always going to have these fixed shift points, and they're also going to be kind of a fixed shift feel, if you will. That's going to be its default if it can't trust the throttle position sensor. A vehicle speed, they don't have a vehicle speed sensor on this. They have what they call an output shaft speed sensor. So we've got a 24-toothed wheel right there on the output of this gear set. This is part of the output gear set right there. And you can see I've got a speed sensor kind of stuck to it. It's electromagnetic. It's a 2-wire sensor. So like here's my output speed sensor and its wiring. And so these little toothed wheels, when they pass by, there's a permanent magnet inside there. When they pass by that permanent magnet, and that changes the flux lines, kind of concentrates them, expands them out when they're in the opening, and concentrates them when that little tooth goes by the tip of the sensor. The fluctuation of the flux lines in and out, in and out, in and out, that induces an AC voltage on our circuit. And what the computer does is it counts the pulses, 1, 2, 3, 4, and it can count how many pulses occur per second and translate that to output shaft speed. Now here's the thing, is different vehicles are going to have different tire sizes and so forth. So there's an adjustment, what they call a pinion factor, and that's going to be in that's going to be a setting that you adjust in the powertrain control module, so that way you can correct for tire size differences. So because this output shaft speed sensor, it doesn't know if you've got 14-inch wheels, tiny little 14-inch wheels, or you got 18-inch rims with big old tire, you know, some decent sized tires. So each revolution of the tire is gonna cover a different amount of ground. So the computer is gonna need to know. It knows how fast the output shaft is going, but it doesn't know how fast the wheels are going, or well, I guess it does know how fast the wheels are going, but it doesn't know how much ground is being covered by the wheels. So that's why you go through what they call pinion factor. And when they adjust the pinion factor, even though pinion factor makes it sound like you're telling it like what ring and pinion you have, when you go into that setting and you change your pinion factor, you actually change tire size options. And so if the speedometer is off, or if you know, you do a dramatic tire swap change or whatever, you would likely have to go in and adjust the pinion factor setting. Now here's the problem. is the only options that they give you are ones that are available for that vehicle. So you can't put any old tire size in there for a pinion factor, and that's kind of unfortunate for people that want to do swaps and so forth. So if you don't have the actual size tire listed when you do the pinion factor, you're probably gonna have to pick something as close as possible. Might have to do some math or something like that to figure out which tire combination, which P size that they have up there is going to match whatever you're putting on as close as possible. More on the speed sensors, we also have a input shaft speed sensor, and you can see down here there's a speed sensor, same thing, 2-wire, variable reluctance, and it measures off of the 60-tooth reluctor ring that's on the input drum. So we have a direct measurement for input shaft. So you can see the input shaft generates 60 pulses per revolution. The output sensor generates 24 pulses per revolution. And they're variable reluctance, 2-wire sensors. So that actually used to be one of the biggest problems that they had on these 41 TEs. The output speed sensor would fail, and it would just refuse to put an output. And it was it's horrible if it did that going highway speeds, because as soon as it failed, it thought you were going 0 miles per hour and it would downshift you into first. And there's no one-way roller clutches or sprags, so you actually went to first gear. But usually the symptoms were low speed, that they would fall in the somebody would be driving at lower speeds, and the output shaft speed sensor would fail and it would drop you into first gear. We still have, these are two of the speed sensors. We have an input speed sensor and an output speed sensor, but one thing that we need to take into consideration too is that we have an engine speed sensor, crankshaft position sensor, so they can look at that, comparing engine speed to input shaft speed to figure out what's happening in the torque converter clutch, and then they can compare input shaft speed to output shaft speed to figure out gear ratios. So if I can measure the speed of my crankshaft, speed of my input shaft, and speed of my output shaft, I know what's happening in the torque converter, and I know exactly the gear ratio that's occurring with the gear set. So this transmission is really easy and quick to set codes if there's like a slipping clutch, or if my torque converter clutch is not working right or something along those lines. It will flag a DTC really quick. These right here are DTCs that will set because of a speed sensor, and 715 and 20 identify speed sensor errors. These right here, the 736, 31 through 6 identify gear ratio errors. So like 731 would be gear ratio error in first, 732 would be gear ratio error in second, and so forth. 6 or 5th or 6th is one for reverse. So they've got all the gear ratio error stuff figured out through these codes. And once again, the way they're figuring out these gear ratio errors is they're looking at the input speed and the output speed, and when they command, say first gear, and it should be 2.73 or whatever it was, if it doesn't get that, it knows there's something slipping, and it'll flag a code. The 740 is a torque converter clutch circuit or failure. If you have one of these codes, like a gear ratio error code, you'll almost always have this right after it, the P1790, or along with it, should say. Fault after shift. If you have a gear ratio error, it'll set a 1790 as well, which basically says we commanded a gear, it didn't work, and we didn't get a gear ratio error, gear ratio that we expected, so we got a fault after a shift. So really, when you look at this diagnostics, you're going to be looking to see, all right, do I have a gear ratio error, a pressure switch problem, something is occurring causing a problem. And then 1794 is identifying the speed sensor ground as an issue, because it is common ground between both of the speed sensors. These next slides talk about the transmission range sensor, and what the range sensor's purpose is to let the computer know what range we've selected: park, reverse, neutral, drive, low, so forth. And also the transmission fluid temp, and also give us information for reverse backup lamps and also the park neutral start safety switch. On the scan data, we see these 4 circuits here listed as an input, and they're either going to say closed or open depending on the switch state. And it says like T41 C1, T42 C2. The reason why they have both of those is because depending on the wiring schematic you're looking at, they might identify as T41 or C1. So it just kind of makes that simple. But between these 4 switch circuits, we can figure out what manual valve position we're in. This is the thing that Chrysler or FCA wants you to do when you're diagnosing these 41 TEs. Is the very first step of diagnostics, and I bolded or capitalized the word first here. They want you to do this very first, is to go through and do what they call a shift lever position test, because they don't want you to go down a dusty road trying to find a transmission issue when all along you had a bad range sensor and it was telling you that you're in manual second or you're in neutral or something like that, and you weren't actually in those gears. So, because the TCM doesn't receive the correct shift lever position, it's not going to give you the gears that you're expecting. If you're expecting overdrive and it thinks you're in 3, it's only going to give you first, second, and third. There's actually 2 different tests, or more than, actually really more than one way you can check this. One is the scan data. If you go into special functions or miscellaneous, you can actually do a shift lever position test, and it'll tell you shift into park, hit enter, shift into neutral, hit enter, shift into drive, and they actually have you go through, and then when you're done, it tells you if it passes or fails. But you could also go through and monitor the switch states and see if they're opening and closing. And thirdly, you can look at and I don't have it up here on the screen, but you could look at the PID that would basically tell you your gear selection and see if it's changing accurately between park, reverse, neutral, drive, all that good stuff. But do this step first before you start diagnosing a transmission. Just verify that it's getting the proper signals as far as the shift lever position status. This is the layout, I guess you would say, of how the switch is set up. It was actually different when these transmissions first came out, but in '96 to the last, when they stopped making this transmission, they pretty much stuck to this little sequence here. Now if you look, I've got what's a sense signal circuit. They put 12 volts and they go through a resistor and they go into that little signal, the circuit. So I'll have 12 volts on the circuit so long as the switch is open. As soon as the switch grounds and I find myself a path to ground, then I'm going to drop all that voltage to 0. So imagine a resistor, 12 volts, a resistor, and then a tiny little voltmeter in front of every one of these circuits. So every one of these would have a little voltmeter and a resistor. And then if you look on the side here, they will tell you when those switches close. So that'll close in park and neutral. This will close in park, reverse, neutral, and low. This will close in park, third, and low. And then this will close in neutral, drive, and low. So I get my 4 little switches. If I look at this picture on the side, these are the terminals, and they're like spring loaded with a little plunger on them. And you might not be able to tell, but you can see where they've kind of been riding on this little plate. This plate will rotate over those switches. So if I've got plastic there, I'm not providing a path to ground. But if I have steel there, I would be able to close that contact and provide a path to ground. So here is the park position, and everything there is basically, let's say everything here. Actually, the park position, let me change that. The park position would be right here, I believe. So these 3 circuits have a path to ground, just like these 3 circuits would. So it's likely that this Sense 4 circuit here is on this path right there. So that is how they operate. And you might not want to take this for face value. I just kind of did that on the fly. I don't know if that's 100% accurate or not, but these 4 switches ride on this metal plate, and when you're rotating this rooster comb or this plate, it's going to switch between making contact and not making contact depending on what part of that it's on. So that's how it operates. So here you can see, like in park, all 3 of these would be at 0 volts because I would have path to ground. And then this would be at 12. And then, so that would be park. I'm just kind of just going through. There's a chart on the next slide, but if I go in reverse, this one would open up, that's supposed to be an R. That one would open up to 12. This one would be 0. This one would be 12. And this would be 12. So going down the line, neutral, this would be 0, 0, 12, 0. I'm not going to do all of them right now, like I said, because there's a chart on the next slide, but you can imagine as you're going through, if this indicates that the shift lever position that you're in, it's going to close the path, and then you're going to see 0 volts on that circuit. So if I'm diagnosing this vehicle and I find that I've got a bad range switch, maybe something's saying 12 volts all the time or something's saying 0 all the time, I might have a bad switch or a short to ground, or if it's staying 12 all the time, I might have an open in the wire or open on the switch. But that gives us an idea of how it works so that maybe we can diagnose it properly. Like I said, here is the chart, park, reverse, neutral, D3. These transmissions, they don't have like a D4, D3, D2, and low. They usually have overdrive, D3, and then low. They skip 2 for some reason. I don't really know why. But now some of these vehicles will have auto stick, so you can go to a manual mode option, but the ones that don't have auto stick and they just shift through it, these are usually the 6 options that you get. There's also a thermistor in there, and I've mentioned that before, but that little stub right there is a temp sensor built into here. So there's a little wire there, a little temp sensor, and that's represented by this on the schematic. So it's a negative temperature coefficient. The resistance drops as the temperature increases, and it will change the voltage on that wire. And based off of that voltage, we're going to be able to figure out what operating mode or what strategy we're going to operate this transmission in. These are the 6 basic modes of operation. And I know these numbers don't quite line up perfectly, but this is what they've got published in their books, so it's what I have put up here. They've got this extreme cold function and relay open limp mode, meaning they operate this transmission in limp mode, and when they turn the relay off, they turn the power off to all the solenoids, and when you do that, you've got second gear, you got park, neutral, reverse, and second gear. That's it. And the reason why they do that is these solenoids are in such charge of the fluid flow that they don't want to take it, with it being negative 16 degrees, the fluid's not going to react like they expected, and they know they won't be able to control it through the solenoids properly. So they just leave you in second gear. They are not going to try to shift the transmission until you get warm or warmer, because the next phase is cold, and it says below negative 12 degrees Fahrenheit, but so I don't know if that's those 2 numbers are pretty close. Like I said, this is what's published, but you know, when we jump up to warm, it says 36 to 80. I think it's probably 12 to 35 degrees, which would make sense. They just, whoever wrote this in their books, kind of didn't proofread that, I guess. I don't know. But in the cold mode, it delays their upshifts, and it has quick downshifts, and they don't turn the torque converter clutch on. You can imagine why, is they're going to try to get heat in this transmission and in the engine as soon as possible. And then even in the warm mode, now this is where the terminology is weird. I would think warm would be where you'd want it, but actually warm is still not warm. It's between 36 and 80 degrees. Our shift points are normal, but they still don't turn the torque converter clutch on. So you can imagine the reason why they do that is because they're still trying to get the transmission warmed up. And once it's warmed up, they call that hot, which to me, I would think hot would be bad, but in this case, hot is good. So that's between 80 and 240. I'm going to have normal shifts, and this EMCC means electromagnetic, no, it's not magnetic, electronically modulated converter clutch. It's just their term for how they're controlling the torque converter. So electronically modulated converter clutch, and you'll see a term like this, PEMCC, that says partial electronic modulated converter clutch, means they're letting it slip. Then FEMCC, that's full electronically modulated converter clutch. So the electronically modulated converter clutch means pulse width modulated, they're just bringing the torque converter clutch on. PEMCC means they're pulsing it to the point where they'll let it slip. And FEMCC basically means they pulse it to the point where it's basically engaged and not going to slip at all. So going back to hot, you can see in the hot mode, they're shifting it normally, and you have normal electronically modulated converter clutch operation. But once you get overheated, once you're between 240 and 260, it might not make sense, but they delay your upshifts again, and then they bring the torque converter clutch on early in third. And that makes sense. Bringing the torque converter clutch on makes sense because, as we know, a torque converter, that is where the heat is generated in the transmission. It creates a lot of heat when we have an impeller spinning faster than the turbine. That fluid gets sheared off. It creates a lot of friction within the fluids, like rubbing your hands together, the heat that you create. So that's where the majority of the heat is created in a transmission. So if you're running in a situation where your transmission's overheating, there's two things. One, you're not cooling enough, or you're generating too much heat. They probably can't control cooling, an additional cooling. It's always going to cool as much as it can anyway. So what they can control is bringing the torque converter clutch on earlier and try to removing some of the generation of heat. Now the reason why they do a delayed 2-3 shift and 3-4 shift is if I'm spinning my engine faster, I'm not putting as much throttle, putting as much load. Two things will happen. One, the speed difference in my input shaft to engine, the stator and impeller speed difference in the torque converter is going to be less, so I'm going to be generating less heat. And the other thing is I'll be spinning everything faster. I'll get more coolant flow from my engine, and I'll get more oil flow from my transmission because the pumps will be spinning quicker. Water pump, transmission oil pump. And that will hopefully translate to less on the engine, less engine heat, and also less transmission heat. So that's the idea. And then they have the super overheat, where you're above 260 degrees, and you're still delaying your shifts, but what they're going to do is bring your converter clutch on in second gear potentially as early as 22 miles an hour, and just lock the converter clutch up in third and fourth. So they're going to do what they can to completely remove the heat generation from a torque converter. And then what they don't have listed here, it's super duper overheat, and that is when they basically pull the car over, open the doors, and you're supposed to jump out because the car is going to burn down. But okay, so there's no such thing as super duper overheat, but still a lot of different shift temperature modes. So why would you have improper shift schedules? Well, if you have extreme cold or cold schedules and you're not actually in that environment, you might want to look at the temp sensor circuit resistance. If we have excessive resistance, it's going to translate that to colder temperatures than it probably really is. Now, in theory, they kind of do these deltas where they look at this temperature, they look at intake air temp, engine coolant temp, and all these different things, and they should be able to say something's not reading right and set a code. But if they don't, that's something that's easy to check by looking just on scan data. The causes for the overheat or super overheat: high engine idle. And now high engine idle, the only way that would really cause it is if you're sitting in traffic a lot with your foot on the brake and your engine idles high. Like if you were to bump it in a neutral or park, it'd be revving up at like 1800 RPM or something. Because if you're sitting there in drive and you've got all this engine speed that wants to occur, you're going to be basically stall testing your converter, and you're going to be creating a lot of heat in your torque converter. Trailer towing, meaning if you're giving a lot more throttle for just cruising and doing everyday driving, your torque converter clutch is likely going to disengage more frequently for the assistance and torque multiplication and so forth. And then that translates to extra heat because of what's happening through the torque converter. If you have an engine that's overheating, and surprisingly it says overcooling could cause that. Overheating makes sense because that's where we're relieving the transmission fluid temp, right? When we get into the hydraulics, you'll see that right from the torque converter, when the fluid pumps through the torque converter and it comes out of the converter, it gets directed to the oil cooler. The oil cooler's in the cold side radiator tank. So it goes in there, and that's hot ATF is going to transfer its heat into the engine coolant. So it's a oil to water cooler assembly. And then that cooled oil will return back to the transmission and go through the lubrication circuits, and then into the pan and then cycled back through. So if I have an engine that's overheating, maybe I'm transmitting my overheated engine into the ATF, or I'm not able to release any of the heat in my ATF because my temperature is so high with the engine. So that one could cause the other. Brake switch problems, a lot of, especially earlier vehicles, when it reads brake pedal input, it disengages the torque converter clutch. So it thinks the brake pedal's applied all the time. You could be driving around without it ever engaging the lockup torque converter, and that is our component that is there to reduce some of the heat in this transmission fluid. The cooler line restriction. Obviously, if we need to release the heat through our oil cooler, if we're not able to flow the quantity of oil through our oil cooler that we need, then we will trap more heat in the transmission, and the transmission might start to overheat. The whole overcooling thing, I don't really know if that is going to be a very common issue. It says below 150 degrees. And the idea behind this is if your engine is operating at too low of a temperature, it might tell the transmission to not lock up the torque converter. And you might have a situation where you're not locking up the converter because it's actually trying to get the engine to have a little bit more let me rephrase that. If my torque converter clutch is not being commanded on, there's two things that are going to happen. One is my engine RPM is going to be a little higher, and two, the heat that I generate in my torque converter is maybe going to allow the transmission to help heat the engine coolant up. Now that typically doesn't happen. There's usually not enough of a radiator to actually deal with that if you're undercooling an engine, or overcooling it if it's below a certain temperature. But like I said, I don't really see these things, the overcooling part, happening too much. All these other things do make sense, especially depending on how you drive it. Engine idle, yeah, okay, especially if you're in stop and go traffic a lot. Trailer towing is obvious. If you know you're going to be pulling trailers, it always, no matter what transmission you have, it always makes good sense to put an external, an auxiliary cooler on it. And engine overheating makes good sense. The restrictions and brake switch problems. The overcooling, okay, maybe I'd have to be proven that, but they do put that in their literature, so I feel it'd probably be a good thing to include on the chart or slide. So those are all inputs. We looked at the pressure switch assembly, the input speed sensors, throttle position sensors, and all that good stuff. Now let's think about some of these outputs. There's only a relay that we look at, and then these solenoids, the solenoid pack. This transmission utilizes 4 solenoids, and looking at the wiring schematic, you can see it's a low reverse solenoid, 2-4 solenoid, underdrive solenoid, or overdrive solenoid and underdrive solenoid. There's 5 clutches in this transmission though, so the one they left off is reverse. And you can, I'm trying to spell reverse here. You can kind of imagine what they're going to do about reverse. Because reverse is only applied when I shift the transmission in reverse. So do I need to be turning it on and off electronically? Probably not. If I just let the reverse clutch apply by shifting through a manual valve movement, when I actually physically shift my shifter into reverse, it moves a valve in the transmission and then opens up the passage to the reverse clutch. And that's exactly what they do, because it's not what we would call a shifting clutch, where it has to come on and off, like when we're going from first to second, second to third, third to fourth, we're releasing a clutch, applying a clutch, applying a clutch, releasing. We don't have to do that on the move with reverse. So they can let that function be taken care of simply by the manual valve shift. So how do they work? Well, we have power coming in, and that power goes to these pressure switches, 1, 2, 3. Then it goes to the 4 solenoids. And the solenoids are going to be grounded by the PCM. They got a transistor in there that provides a ground. And there's quite a bit of sophistication that occurs, because all of the shift feel, the whole shift quality that we have on these transmission shifts, are done through these solenoids. They pulse with modulate them. You hear them clicking. You hear them click and ratchet. And when they're doing that, they're pulsing the fluid into the circuits. So we'll see more on that when we talk about the hydraulics. Here we're looking at the electronics of it. So they are PCM ground controlled. Power is fed by a relay. They're pulse width modulated. And here, like I mentioned, not only to control the fluid flow to the clutches, but also to regulate the current flow to them. If I hooked my ohm meter up to these solenoids, there's barely any current flow, or barely any resistance to these solenoids. There's around maybe a little over an ohm. You can kind of tell by looking at these. You might be able to tell at least by looking at the picture. They're pretty thick windings on there. And if you energize them directly, you'd probably pass 10 amps or more through each one. So you would never want that to happen. It'd be such a huge electrical demand on this solenoid block. So what do? They pulse width modulate them to get the flow through the solenoids like they want it. And then once the shift is done, and if they need to leave the solenoid on, they'll pulse width modulate it just enough to hold it in its position. We have codes that represent the driver circuit failures. This is the thing, if you're driving down the road and you're going highway speeds or so forth, and this thing fails, the solenoid pack fails, they're going to attempt to shift you into neutral, because they don't want to downshift you into first gear or even put you into limp mode. Limp mode's second gear in this transmission. So all the solenoids are naturally off in second. But if they can prevent, like if you're cruising 60, 70 mile an hour down the highway and it has to shut down, it's not going to want to just slam you into second gear, because that would be you might bounce your head off the steering wheel or something like that. That would be bad. So what do? If it can, it will put you into a like maybe, well, whatever gear it can. I'm sure the light would come on, and if the first time, once you slow down below 45, it puts you into relay open limp mode, where they turn the power off to the relay, and we lose power to our solenoid pack. This is one of the things that you'll see when you're looking at these solenoids on a scan tool. It's kind of neat. The PCM will monitor these by pulsing about every 10 seconds or so. They will turn the solenoid on and then back off, and they will look for an inductive kick. If you've been through engine performance class and you've learned all about fuel injectors and you learned about ignition coils, you know that when you create a magnetic field and then you remove power from that magnetic field, the collapse of the magnet, I said that weird. If you power up a coil, you create a magnetic field, and when you unplug that coil, that magnetic field collapses around that coil and induces a voltage into that circuit. And that voltage that will induce will spike up, especially if it doesn't have a path for it to flow. I mean, if I don't have it grounded out, if I don't leave a jumper wire or something to jump the leads together on. When it's disconnected, that magnetic field, as it collapses, the flux lines cut across the conductors and they induce pressure into those coil windings. So it creates a high voltage kick or a spike. Well, if I've got a bad coil, I won't create it if I have an open coil, because I won't be flowing current. If I have a shorted coil, it would bypass those windings and it would not create a strong magnetic field. Or if I have high resistance in the circuit where it's just not flowing much current, if I can't get a strong magnetic field, when I shut it off, I won't have a strong inductive kick. So what they're doing here is they're constantly checking these about once every 10 seconds. They'll turn the solenoids on, turn them off, and they'll look for an inductive kick. If they see the inductive kick, it goes over a certain point. You can see on this red that 40 volts is a little over 40 on this one. Probably about the same on these. So if they're looking for that inductive kick, if they see it, then they know the solenoid has some electrical integrity. They can't really prove that it's good and perfect, but they can tell that it's not short, or it's not open, or it doesn't have extreme, it doesn't have very high resistance. So yeah, if it fails any one of those tests, then they know they've got a problem. Here on this one, you don't see the inductive kick. And this is the underdrive solenoid. You could tell where they were testing them. They were testing all of them, but we're missing our kick. So we either have a bad solenoid pack, or we might even have a bad computer. Because if that driver can't control it properly, you're looking at a computer as a problem. On our scan data, we can see the activity of what's going on. They still kind of have this messed up a little bit. When I was taking these screenshots, they called everything a sensor, even if it was a solenoid or whatever. Everything was called a sensor. I haven't checked it recently to see if they fixed that, but for well over a year and a half, they hadn't changed that. And another thing that I thought wasn't very good on their part, which hopefully they get a little more specific with, they say low reverse, low lockup clutch, 2/4 kick down, low reverse clutch, overdrive clutch. It makes you think you're looking at these clutches, but these are all solenoids. They need to put the word solenoid behind it, because the applied and not applied is going to be referring to is that solenoid on or off, and in reality they should say on or off instead of applied or not applied. In these solenoid packs assemblies, this is I took one apart, or in these three pictures you can see it disassembled. These are the coils, as you can imagine. Those are the 4 solenoids: low reverse, 2/4, overdrive, underdrive. And then these little plungers right here, those are the pressure switches. I have 3 pressure switches. When you take the plunger off, you can see there is a brass plug and a spring. And what you can't see very well is there's another brass ring in there. So these springs push these plungers away from the brass ring, and then when you get pressure in there, the pressure that comes in there will push the plungers down and make the edge of the plunger contact the ring right in there. And that grounds the circuit out. I know it's kind of a weird way to draw all this stuff, but this, if you flip this over, the springs are kind of, like I said, they're right here, and they're holding these plungers off of the seat. And then once pressure comes in and pushes that plunger down and lets the edge of that plunger contact the seat, through the little plunger and the spring, they're able to ground it out right to the cover. So that's how it works internally. It's easier to probably understand just by looking at the schematic what's going on. If I follow my voltage, I got 12 volts coming in. I go through a resistor, and then I'm going to be picking up that voltage right here at the sense circuit. So like right now, all of these you would display 12 volts on, right? Because none of these switches are closed. Now if pressure came in and closed, this is the overdrive switch circuit. If pressure came in and closed the overdrive switch circuit, I'd have 12 volts in the beginning of the resistor, but I had 0 volts on the outlet of that resistor, so this would then change to 0 volts, and it would be giving me an indication to my PCM that my overdrive switch had just shuttled and changed. So it's going to sense either 12 volts if the switch is open or 0 volts if the switch is closed. The pressure switches really feed information to the powertrain control module, and it lets it know how quick these circuits are filling up. They're not sensors. You can tell there's no variation to it. It's either an open or a closed circuit. So it takes about 20 or so psi to close those switches. And once you've got that pressure in there, 20 psi, it closes the switch. It gives an indication of how long it took for that solenoid to fill the circuit up. And then they can make some adjustments. They can base that information and do some lookup tables and do some adjustments in the transmission so the solenoids will operate properly. Here we see our pressure switches. They've displayed on the scan data. They're showing them as open or closed. So if you're having an issue with a pressure switch error, you can look at your scan data here and see if that state ever changes. Now realize that these are the pressures that we need to be in low or reverse for this pressure switch to close. And actually, hold on a second. Now I'm thinking about it. Actually, it only works in low. They shouldn't call it a low reverse pressure switch. It's really a low pressure switch. And the 2-4 pressure switch will only close when I'm in second or fourth. The overdrive pressure switch will only close when I'm in overdrive. They don't use an underdrive pressure switch. I don't know why. Maybe they ran out of wires. So they have an error counter, so that, and they're not always going to freak out if one of these things flicker on and off. You know, there's, I'm sure, situations where bad connections are made, but they do also have an issue with these transmissions of setting mismatch codes where the pressure switch is either open or closed and it shouldn't be, and those can cause transmissions to fall into limp mode, come back with codes, and a lot of technicians struggle with those codes. A lot of times they end up falling back to either one of two things: poor connections, not necessarily in the transmission, but the connector itself. And then the other possible problem is valve body wear. When you get cross leakage occurring because of valve body bores are worn out and so forth, they can erroneously cause the pressure switches to open or close when they shouldn't be. And we'll see more of that when we look at the hydraulic side of things too. More on the solenoid block there. It takes about 20 psi to close those pressure switches. And we do have these DTCs, as I mentioned. The sense circuits could throw these 3 codes, and if I've got pressure related codes, or if they suspect that I'm not getting hydraulic pressure when I should for these particular gears, they could set those 3 codes as well for pressure failure. As far as diagnosing the solenoids themselves, I can actuate these different solenoids, and here you can see on this slide right here, if I'm going into like actuator tests with the scan tool, I can operate these solenoids through the scan tool, and I could do some measurements as needed. So those are my 4 solenoids that I have in the transmission. So if I need to operate something with the scan tool hooked up, amp clamp, or I should say a DVOM, amp clamp or DVOM or scope hooked up to it, or I'm going to listen to it, you can actually go in and energize these solenoids independently through the scan tool. And this screen right here is showing an example of like the low reverse solenoid. It's toggling it on and off 1 second at a time. So it's on for a second, off for a second, on for a second, off for a second. Here we're looking at the transmission relay. Relays aren't that complicated, but they have a few inputs to let it know that after the relay closes, we've got a couple inputs to let it know that the voltage is finding its way through. If they command the relay open and it still sees voltage, it'll set a code for powering up all the time, or relay stuck closed should say, or short to voltage. Or there's also the situation where if they never see voltage and they command this relay on, then it would be a bad relay. They would have a circuit for an open circuit or possibly a open relay contacts. It is a power side controlled relay. So they put 12 volts out to it from the PCM, TCM, and that energizes it so it has its own like external ground. That way they're limiting the amount of potential failures. Like if you're going to have a short to ground, in this case, the short to ground would not energize this at all in this function. Whereas if you had a short to ground and it was ground controlled by the PCM, you would leave the relay on all the time. So this is a way to control power to the solenoid pack. We got power coming in through the relay, has some sense circuits, and then this goes right into that solenoid pack and powers up the solenoids and the pressure switches. As I mentioned before, we got a relay always off, relay always on, and then even low battery voltage. They can sense obviously the battery voltage and set a code for it too. Here we're going to talk about clutch volume index, and this is FCA's fancy term for shift adapts or transmission adapts. CVI, as its name implies, clutch volume index, it's going to be a number that represents how much fluid it takes to fill this clutch assembly up and before the clutch actually starts to apply. And the idea behind it is if I energize a solenoid, and this is where the pressure switches come into play too. If you remember, the pressure switch is closed at 20 psi. Because if I fill a clutch assembly up, let's just pick overdrive for example. If I energize the overdrive solenoid and I'm filling up the overdrive clutch, by the time that pressure switch closes, I know that I filled the whole clutch circuit up with ATF, and I know that the piston has moved and taken out all the clutch pack clearance in the overdrive clutch pack, and I also know that the accumulator hasn't really started to stroke yet. Because at about 20 psi, I've taken up my clutch pack clearance, I've filled all the circuits up with fluid, and I'm just about ready to stroke my accumulator. So then at that point the pressure switch closes, and the computer now knows how long it took for all that to happen. From when they commanded the solenoid on to when the pressure switch closed, it was a piece of information that told them how quickly this clutch circuit filled, didn't stroke the accumulator, yet moved the piston in the contact with the clutches and took the clearance out. From there, they can go through and tweak the transmission solenoids to get the shift quality where they need it. And the CVI, this clutch volume index, is going to be a number that is going to let us as a technician know if they're trying to compensate for a transmission that takes way more fluid than it probably should to apply clutch, or if it's slamming into gears, this can be way less. So it's a random number. It's almost like fuel trim, if you will, for fuel management, but the numbers aren't as easy to memorize or remember. So these are the normal CVI values for the 4 clutches that we use and can control in this transmission. So each one of these are solenoid controlled. If you look, 35 to 83 for low reverse, 20 to 77 for 2.4, 24 to 70 for underdrive, and 48 to 150. So those numbers are kind of, like I said, they're pretty random. I don't know why they couldn't just make them 0 is perfect and plus or minus, like fuel trim, but they did what they did. The only thing I could think is, like, if I put a 0 behind everything and said, remember how I was saying milliseconds, about 400 milliseconds is a normal shift? Like, maybe this is a time. This is all opinion. I don't know if this is true or not. But if they obviously don't, they don't list this extra 0 on the scan data. But if I had a slow, if I had a shift that was like a clutch that was coming on slowly and causing my shifts to be kind of delayed, my number would be higher. If I was slamming in a gear, banging in a gear, coming in way too quick, the number would be lower. So that might help you remember it, I don't know, because typically what's happening if you have a low, if you check in the CVIs on a scan tool and you see the number to be low, like I'm gonna use 2.4 as an example because low reverse usually isn't that big of a deal. But let's say I had 20 a CVI on 2.4. Well, I'm probably slamming into that gear every time I shift from first to second or from third to fourth, because 20 is the low end of the spec. If I imagine if that's taken 0.2 of a second or 200 milliseconds, so anything that's occurring or showing a low CVI is going to be the clutch is applying too quickly. I've got high pressure in the transmission, my accumulators are stuck and not stroking, a broken snap ring where maybe my clutch pack clearance is already taken out and I don't have any accumulation or a cushion that's occurring through the clutches that naturally occur. If I'm way up there towards the high end of the CVI number, that means it's taking longer. Like imagine if this took 770 milliseconds to apply. That's a delayed, that's not delayed, it's a slow or a soft or a slipping type shift. So then we looked for things, high CVI values, we'd be looking at things that would take longer than normal. Worn out clutches, leaking seals, a pump that's not producing the pressure or low pressure, clogged filters, those types of things. So you can kind of imagine if we're looking, if we're diagnosing a transmission and the customer comes in and they say we have yeah, this thing seems like it's slipping, that doesn't feel right. Well, I could look at those CVI numbers and say, yeah, that overdrive clutch, it's maxed out on its CVI. It's way up there at the maximum of its adapts. You're not necessarily setting a code and you're not in limp mode now, but yeah, this thing's probably on borrowed time right now. So the CVI values, the adapts, are actually a pretty good indication of how this transmission is wearing, if you will. Now this is the thing, whenever you go to rebuild a transmission, you need to reset all these, because it takes a while for this stuff to learn, and if it was adapting to a slipping transmission and then you fix the problem, it's going to be slamming hard into those gears next. And so if you reset these, it kind of normalizes these numbers and then it can learn, and that's the process called Quicklearn. Here we see the CVI on this charger that we have in the lab, and you know, these numbers aren't too crazy. I like, once again, I don't like how they have their numbers because they're hard to memorize, but the overdrive looks high, but if you remember, I think that one was allowed to go as high as 150, so it's probably not too bad. Most of them were between like 30 and 70, so in this falls in that kind of range right there. So yeah, you could look in these at the CVIs for a transmission and get an idea if you're at the extremes of one of the CVIs that maybe you have a problem with one of those clutches. When do they update? This is the thing, they don't constantly update. Like we think of fuel trim on a vehicle where you're driving down the road and it's always providing an update for looking at the O2 sensor, and it's always tweaking. Short-term fuel trim is following the O2 sensor, and then if it learns a trend and transfers that over to long-term fuel trim. Well, they don't really do that on these. They concentrate basically when the solenoid goes from, or I should say a clutch is going through a shift. When we're shifting from like I'm gonna use underdrive as an example. Underdrive is applied in first, second, and third, and it releases in fourth. So really the only time underdrive is going to update is when we're downshifting from like fourth to third or fourth to second. So we look at the first time that clutch goes from an off state to an on state, and they'll adapt off of that. So here we look at this example, the low reverse CVI is going to update on a 2-1 or a 3-1 downshift. And it'll only do it, this is weird, they don't all do this way, but they'll only do it between 70 and 120 degrees. So my low reverse clutch is applied when I'm in park and neutral and shift it into first. It's already applied, so they don't want to update anything if I'm moving my manual valve or doing any of that. So once I shift out of first and I'm in the second, and maybe I shift in the third or fourth or whatever, the first time the computer is really in charge of applying that clutch is when I'm slowing down to a stop sign or a stoplight and I go to a 2-1 or a 3-1 downshift. Then the computer's in charge of it, and it can go ahead and look at how things happen and adjust the CVI based off that. 2.4 CVI is going to update on a 1-2 shift, and pretty much for 110 degrees and up. So if we think of what's going on there, the first time the 2.4 solenoid or clutch, no, first time the 2.4 clutch is actuated with complete computer control would be on the 1-2 upshift. So you might as well update it on that, and that's what they do. The underdrive clutch, the first time, as I already mentioned this, it'll be on a 4-3 or 4-2 downshift, because the underdrive clutch is applied when I shift it into drive, but they're not going to want to update it on anything where I'm physically moving my manual valve on. That the results would probably be too varied depending on how I'm shifting it. So the first time the computer's in charge of shifting the underdrive clutch would be once I'm in fourth, when the clutch is released, underdrive clutch is released, and I downshift in the third or in the second. That's when the computer is actually applying that clutch, and it can base its information off of that. And finally, the overdrive CVI is going to update on the 2-3 upshift, because that's the first time when I shift from second to third. That's the first time I go from an off state to an on state with my overdrive clutch. Those are CVIs, clutch volume index, and they will update for the most part. Other than the low reverse, they'll always be updating when you're driving on the road and occurring these and doing these shifts when the clutches go from an off state to an on state, and the computer's in charge of it. They do have Quicklearn function, and I mentioned that a couple slides ago. When you do a Quicklearn, it's because you've changed some of these parts that could affect the shift adapts. Anything that could affect your shift adapts, you'd want to go through a Quicklearn. So rebuilding your transmission or replacing a transmission, replacing the solenoid pack. If you went into the transmission and replaced the valve body or overhauled the valve body, bored it out, put new valves in, put a shift kit in it, whatever. Anything that you've modified on this transmission that could potentially affect how this transmission is going to shift, you're best off going in there and doing a Quicklearn. Should you do a Quicklearn if you look at, car comes in, these adapts are out of the range? Should you do a Quicklearn and reset them? Probably not, because that transmission's been adapting over time and got to those numbers. If you don't fix the transmission or take it apart, or at least attempt to fix something, there's no point in Quicklearning it, because it'll probably operate worse until it can adapt back to where it was. It's kind of like if you were to reset fuel adapts without changing anything in the engine management or fuel injectors, fuel pump, whatever. Resetting the fuel adapts, that's not going to accomplish anything because the problem still exists. These last few slides, later on in this transmission's lifetime, they've made some adjustments to it. You'll see when we talk about in the hydraulics that this transmission had fixed line pressures all the way up until, I don't know, mid-2000s or so. And then they added a line pressure solenoid, and that line pressure solenoid gave them the ability of changing line pressure up and down as needed. Well, with that came some valve body changes, some electronic changes, and so forth. Now, this slide right here actually doesn't show anything that's different or new. I just got basically the schematics that you would find on the LPS line pressure sensor or solenoid, line pressure solenoid version of the 41TE. It still uses two speed sensors, and they're both variable reluctance. It still uses our Prindle switch that gives transmission temp, and it has our 4 circuits to indicate Prindle position. The solenoid's no different. We still have 4 solenoids, 2-4 low reverse, underdrive, overdrive. They're still controlled by the PCM, so there's really no difference there. Here's where we see a little bit of a difference. Now we've got our powertrain control module, and it's going to control the what they call an assembly line pressure sensor variable force solenoid. Kind of a mouthful there, but we basically have a pressure sensor, of not just a switch, but a sensor, and we also have a solenoid. And you can see the PCM is going to be able to control the line pressure solenoid. And we also will have a 5-volt supply and a line pressure sensor. So we'll power up this through this assembly line variable force solenoid assembly. We're going to have the ability of controlling a solenoid to alter the pressure in the transmission, and then we're going to have a sensor in there that's going to be able to monitor the pressure just so that they can control the solenoid properly. It's a feedback type system. So this information is going to feed the computer with the pressure that we have. The computer is going to change the duty cycle, whatever it thinks it needs to be for the line pressure solenoid. And if they got the pressure that they wanted, how would they know? Because the line pressure sensor will report whatever the pressure the transmission is generating. So they can tweak their duty cycle to get what they want. It's a feedback type system where they command a duty cycle, they wait to see what pressure it generates, and then they adjust, the PCM adjusts the duty cycle until it gets the pressure that it wants. So there'll be an actual pressure and a desired, and they should match in this a line pressure type system. But anyway, I wanted to show that because this transmission has been out since 1988 and a half. It's an old transmission. It's been around for a long time, and it's lived a long life. I mean, I don't know when the last year. I could probably dig that up, research that. But you know, even the 42, you saw that 2010 Charger that we have out at school, that has a 4-speed version of this. I want to say the Jeep Wranglers in 2018, 2019 still use this. So the 4-speed transmission version, the rear-wheel drive version of this. So anyway, they didn't do much to it. In '96, they made some changes in the electronics. They improved the software, and they improved the computer, the hardware itself, quite a bit. But then it was a pretty solid transmission throughout its lifespan, and they've just recently, well, I shouldn't say recently, but in the mid 2000s, that's when they started adding these, the ability to change line pressure and so forth. And really, what they did, it wasn't giving them the ability to raise the line pressure. It allowed them the ability to lower line pressure, because this transmission in its life was quite a bit like the Honda transmissions, where even at like in first gear and second gear, you can have at idle, you would have 140, 150 psi. Well, that's a lot of pressure if you don't need it. So the idea of adding these line pressure solenoids is the ability to, instead of having it sitting there at low throttles or at idle, cranking out 150 psi or 140 psi, they'll go ahead and lower that pressure down, and then they'll raise it up to that 140, 150 if you need it, but otherwise they'll keep it low. And that's the idea of the line pressure solenoid addition on these transmissions. It's really more to lower the pressure so you're not generating more pressure you need, because that's more drag on the engine, and that steals a little bit of the economy from the engine. So anyway, this presentation right here is half of it, if you will. It's on the power flow of this transmission, on the electronics, and then the next presentation will focus on the hydraulics of the transmission, and it will also talk a little bit about the rebuilding parts and uniquenesses that it might exist if you guys ever choose to go through one of these transmissions.